Now we continue to learn Chapter 2, Determinants. For the determinant of matrix, we consider Part 2, Determinants and Properties. For 3 by 3 matrix, we can denote determinant A like here, and we can compute like here, which defined by A11 times determinant of M11 minus A12 times determinant of M12 plus A13 times determinant of M13. Now, how about for general n by n matrix? So the determinant of an n by n matrix A denoted by determinant of A is a scalar, is a number associated with the matrix A that is defined inductively as here. If n equals 1, 1 by 1 case, then determinant A just equals A11 itself. And if n greater than 1, then we can compute determinant A by A11 times capital A11 plus A12 times capital A12 plus T plus A1n capital A1n. Here, capital A1j defined as minus 1 power 1 plus j times determinant of M1g, for g varies from 1 to n, are the cofactors associated with the entries in the first row of A. So here we define a new term, we call it cofactor. So capital A1G is the cofactor of small a1j, which defined as a sign. The sign is minus 1 power 1 plus j here, and here determinant of M1G is just the determinant of an n minus 1 by n minus 1 matrix, which is obtained from A by deleting the first row and the just column of A. So we have this cofactor. After we define cofactor, we can just define determinant of A by this formula. A11 times cofactor A11 plus A12 times its cofactor A12 plus T plus A1n times its cofactor A1n. So this definition is given by induction. For arbitrary n by n matrix, you can compute its determinant. You can define its determinant by determinants of n minus 1 by n minus 1 matrices. See, just here. Okay, now we have this theorem. If A is an n by n matrix with n is no less than 2, then determinant of A can be expressed as a cofactor expansion using any row or any column of A. So determinant of A can be written as AI1 times its cofactor, capital AI1 plus AI2 times its cofactor, capital AI2 plus T plus AN times its cofactor, capital AIN. So here we use the ith row cofactor expansion. And also we can use column expansion. So determinant of A also equals A1j times its cofactor, capital A1j plus A2j times its cofactor, capital A2j plus T plus ANJ times its cofactor, capital ANJ, for any I or any j. Now we see a simple exercise. Ask you to evaluate this determinant. So this determinant of a 4 by 4 matrix. How can we compute it easily? So because the determinant of A can be obtained by using cofactor expansion along any row or any column, so we should choose the row or the column which has most zeros, right? So here you see for the first column, there are 3 zeros and only 1 non-zero. So of course, we will choose the first column to make this cofactor expansion. So this determinant equals 0 times its cofactor plus here 0 times its cofactor, and also plus here 0 times its cofactor, plus 2 times the cofactor corresponding to this A41 entry. Okay, and then you will consider this cofactor. First, the sign is minus 1 power 4 plus 1. 4 means the row, right? 1 means the column. So the sign should be minus 1. And for the determinant of M41, so this 3 by 3 submatrix, okay? Say this a third column in this submatrix. This column has only one non-zero entry, 3 here. So you further do cofactor expansion. For this 3 by 3 matrix, we will choose the last column, the third column. So it will be 3, right, times its cofactor. So now the sign should be minus 1 power 3 plus 3. So it's a plus, right? It's positive sign. And then the submatrix here is only 2 by 2 matrix. The 2 by 2 matrix, you can compute its determinant very easily, right? Just as 2 times 5 minus 3 times 4. So it's minus 2. So eventually, this determinant should be minus 1 times 2 times 3 times minus 2. So it's 12. Now we consider the properties of determinants. The first theorem, 2.1.2, tells us that if A is an n by n matrix, then determinant of A transpose, here, A transpose equals determinant of A. So this theorem can be obtained easily by mathematical induction. So when it's 1 by 1 matrix, of course, A transpose equals A. They have the same determinant, of course. And you can assume if n equals k, this conclusion holds. And then you consider when n equals k plus 1. Using the definition of determinant, using the theorem we know before, determinant of a matrix can be obtained by cofactor expansion along any row or any column. You can get this one easily. Okay, now we see the next theorem, theorem 2.1.3. If A is an n by n triangular matrix, then determinant of A equals the product of the diagonal elements of A. So for this theorem, we can also show by cofactor expansion. Because it's a triangular matrix, so for example, you first make cofactor expansion along the first column. Here, only 1 entry is non-zero, and you will get this 1 entry times the cofactor. The cofactor is obtained by a signal, right? The sign should be minus 1 power 1 plus 1 is a positive sign. And then its remaining submatrix is just deleting the first row and the first column. You will still get a triangular matrix. So repeat this procedure, you will get this determinant of A just equals the product of the diagonal elements of A. Okay, so use the column expansion for upper triangular matrix. And for lower triangular matrix, you can use the cofactor expansion along the row. Okay, now we consider this theorem 2.1.4. Let A be an n by n matrix. Determinant of A equals 0 if A has a row or column consisting entirely of zeros. So this theorem can also be shown by mathematical induction, this one. And the next statement means that A has 2 identical rows or 2 identical columns. Also indicate that determinant of A equals 0. So all these 2 statements you can prove using mathematical induction. Okay,